privacy tutorial, and on that page I have a link to the set of slides that I'm going to use today. There's also some material from the previous time I gave this, which was in Seoul, and the material has been updated slightly, so I would recommend you grab the latest set of slides. Okay. So to start, what I'm going to do today is go through an overview of why DNS privacy is important, and why privacy on the internet in general is important. I want to chart the huge amount of progress that's been made in the last 3 to 4 years in this area for DNS, and I want to give you a snapshot of where we are now and what's coming up in this area. So these first few slides are ones that I gratuitously borrowed from Daniel Kahn-Gilmore, who presented this with me in Seoul last time but wasn't able to come today. So I will try and channel DKG as I present this. One of the arguments we wanted to make first is, why does privacy on the internet matter at all? And the answer is that it can be used, surveillance can be used as a tool for social control in ways that aren't immediately obvious. Now, this is a picture of something called a panopticon, which was a prison designed in Victorian times. And the idea behind this building was that it was a circular building and a single guard could stand on a turret in the center and see hundreds of prisoners who were easily in his view, to give one or few people control of many. And we're in a similar situation with the internet today, which is that if you have a viewpoint somewhere on the internet, then that gives you access to the activity of uncountable people, depending on where that viewpoint is. And also the kind of machine learning we have today that means processing that data is completely feasible. One of the counter arguments about worrying about surveillance is, well, I'm a law-abiding citizen. I don't do anything wrong. I'm not worried about being surveilled. I'm really not. But there's been some really interesting research to show that just the fact that you think you're being surveilled actually changes your behavior. So the experiment involved of getting people who thought their behavior wouldn't change under surveillance, asking them questions, some of which their answers were in the majority, and some of which their answers were in the minority, and doing it into 2 sets of conditions, one where you told them they were being surveilled and one where you told them they weren't. What happened was, that bottom line you can see, for the answers where they were in the minority, the ones that thought they were under surveillance changed their answers. So what we're seeing is a direct, if unconscious, effect of the act of mass surveillance of people. In the bigger picture, we know the whole of the internet is not watertight. It leaks information through a variety of mechanisms. It can be traffic analysis, it can be timing. 2 of the most important ways it leaks today are through the DNS, which I'll talk about here, but also through the fact that the SNI in the TLS handshake goes in the clear. So one set of arguments that's been circling around for quite a while is, well, there's no point in securing the DNS if the SNI is still going to go clear text. But one thing I do want to mention is that all the work that's been done to move towards private DNS in the last 3 to 4 years is now changing the discussion in the TLS working group about how important it actually is to encrypt SNI. And although it's a really tough, intractable problem, in the last 6 months there has been a big move towards it. Even though it's not part of the base TLS 1.3 spec, there are separate efforts to now try to do that. So what I'll talk about today and what I'll focus on is DNS, but what we need to be doing is having a concerted effort to fix all these leaks out of this boat in order to make the internet a safer place. So I'll move on and talk a bit more about where the IETF has come into this and where the DNS working groups have come into this. So a potted history of privacy considerations in the IETF. Work actually started on this back in March 2011, when the IAB worked on a document about privacy considerations for internet protocols. Now, you're all probably familiar with, when you read an RFC, there's a section at the end that says security considerations, and that's been there for a long time. The goal of this document was to create a foundation for adding a privacy considerations section at the end of every document to show that the development of that protocol had taken privacy into account. Now, being the IETF, it took a couple of years to get it to be an RFC. And the month before this document was published, a chap you may have heard of called Edward Snowden revealed what the NSA had actually been up to in terms of mass surveillance. So it was an interesting timing, because what was in some ways, a rather theoretical document suddenly became incredibly real and incredibly pertinent. And in fact, you probably know that in response to the Snowden revelations, the IETF came back with a second document with a title that pervasive monitoring is an attack, stating that that attack is on both organizations and internet users as individuals. That document went one step further. And what it actually said is, from this point on, pervasive monitoring needs to be mitigated in the design of new protocols. So this was a change of stance from the IETF and recognizing that this really was an issue and that moving forward, all protocols had to have this as part of their design. So back when this was all happening around 2013, I want to give you a snapshot of the state of DNS privacy at that time. And that really, to do that properly, you actually need to go back even further back to when DNS was originally developed. The RFCs for DNS were published 30 years ago. So if you go mentally back in your time machine, you know, your DeLorean, your TARDIS, your whatever you want, and think about what people imagined the internet was going to be 30 years ago. They had absolutely no idea of what it would become today. So the design goals involved in the original DNS specs were primarily availability, redundancy, and speed, and those were the key things that mattered. Additionally, DNS, in privacy terms, is something that's called an enabler. It's not a service in itself, it enables you to access other services. So it was kind of rather neglected in this sphere because it wasn't seen as a direct service. So as you well know, the standards for DNS originally said use UDP, and they used TCP only as a fallback mechanism when responses were large. So as a result, for the past 30 years, all DNS queries have gone clear text over the wire. So this became very evident how easy we were making it for organizations to do mass surveillance because they didn't have to go and talk to operators. All they had to do was sniff the wire and they could see everything that was going on. Now, additionally, one of the things about the DNS is that there's been a long-held perception that the DNS is public data, in that it doesn't hold anything personal, it's not sensitive, and so there are lots of questions about why would we bother to encrypt it? It doesn't fit into that sphere, and I'll come back to that later. So this is a sort of how does DNS work 101, and where does the data leakage start? So this is a very simple model of how a DNS query works. You have a stub resolver typically on an M machine, like a laptop or a phone. It sends a full query to a recursive server for something it wants to look up. And the way the DNS works is that that recursive resolver then walks through all the authoritative servers it needs to get the answer, but it sends the entire query to every single one of those authoritative servers. So right off the bat, we have data leakage here because the root server doesn't need to know the full query to be able to delegate to the servers that run .org and so on, right down the authoritative chain. So this was done because it slightly simplified the design, but it's quite symptomatic of the way the DNS just didn't put privacy first in any of its design considerations. So things got a lot worse a few years ago with the addition of something called eDNS 0 into the DNS protocol. Now, this was actually a much needed extension because inside DNS queries and responses, you really only had DNS data. This was an extension mechanism which allowed flexible data to be added onto the end of a DNS packet to do really important things like signaling the MTU path to figure out when you needed to fall back to TCP, or signaling server capabilities, something that's really rather lacking in the DNS. However, because this was so flexible, it meant that it could also be used to do other things. For example, embed information about end users into that DNS query. There are two examples of how this has been used. Both of them were done from the viewpoint of somebody, an operator, wanting to provide better service to their end customers. And this provided a really natural way to do it at the time. The problem was really with the implementation. So two examples of this is one is how some ISPs chose to implement parental filtering. And another mechanism is the way CDNs do geolocation. So in the first case of parental filtering, what happens is you want to set up some rules and you want some DNS queries to be blocked. Now, what you might think is that your ISP who gave you your home router would put the logic in the home router and then everything is encapsulated within your home network. Turns out not everybody implemented in that way. In fact, quite a lot of people didn't. What they did was they put all the logic in the recursive server, which meant to make this work, they had to embed in every single DNS query going from your home router to their recursive, some piece of identifying information about who was doing that query. Now, if you were lucky, they used some sort of hash of an identifier. So it obscured you specifically, but it allowed identification of multiple individuals behind a single router. If you were unlucky, they did something like put the MAC address of the machine that was doing the lookup in there with some other information. The worst cases I've seen are usernames being plopped in this little extension. And remember, this is going clear text over the wire. And this was all done with non-standard extensions. So this is where a noble piece of protocol design allowed for a misguided use of part of the protocol. In the CDN case, this is between the recursive and the authoritative, so it's not revealing as much information. But the idea here was that if an authoritative that was going to serve you content knew something about the geolocation of the user that originated the query, then the answer could be customized so that it directed that user to their nearest geographically located server, so they got the fastest service they could. I mean, nobody likes their cat videos buffering, right? So this is a great idea. It's wonderful. Go to the server down the road, not the one on the other side of the world. So again, it seemed a natural fit to tag a subnet, client subnet into the eDNS 0. But again, this is just compounding the problem of data leakage up on that recursive to authoritative leg. So when you use the DNS from home, you might think your queries are really rather anonymized, but the reality is you're behind a NAT and you don't have anonymity. There are many cases where individuals are being fingerprinted. And similarly, even right up to the authoritative servers in the DNS, information about activity is being leaked. So, and remember what's going over that link. It's information about, where you go, what sites you go to, what you do when you get bored, all sorts of personal information is going clear text. But think about it, pretty much every activity on the internet starts with a DNS lookup. So it really isn't just for names. Try it. Fire up TCP/dump and Wireshark looking at port 53 and just watch how much traffic goes out of your machine as you just surf around and send email. Because every time you send an email, you need to get an MX record. So that reveals the domains, email domains of the people that you're emailing. Every time you go to a service, you do an SLV lookup. So this reveals the variety of services you use. OpenPGP key is a nice standard way you can secure email with Dane, but that reveals the entire email address of the contact you want to email. And the problem here is this is only going to get worse. People are putting more and more in the DNS. We're not in any sort of scheme where we're trimming what goes in the DNS. Advantages have been seen in lots of places. So all your activity is being sent clear text through your DNS queries. And because it's being tagged with user identifiable information, I hope your spidey senses are tingling in the sense that what you do, it's out there clear text on the wire in a way you really might not have realized. So that's really the picture. We're talking about what goes over the wire. There's an entirely separate concern about what happens when it hits the servers. Of course, so most people here use an ISP, and you have to ask yourself, who has access to the data that your ISP has? Is it strictly the ISP? Is it the government of your country? Is it security services? Who else is it? Also, who does your ISP share your data with and under what terms and conditions? Equally, there have been cases where ISPs have these huge data stores and they get breached. So how much do you trust your ISP to keep your data secure? Now, of course, all these concerns change as you move from your home, where you're using your ISP, to your work, where you're in an enterprise situation, to a coffee shop, to a hotel. And in every one, all the privacy considerations change. And that not only applies to the recursive, but as I said, also up to the authoritative, because the data leakage goes that far along the path. So what's happening in the DNS is we're leaking metadata. Okay, so we're not leaking your bank account password and email address, but we're leaking who you bank with. We're not necessarily leaking what you buy, but we're leaking where do you shop, where do you go for your entertainment, the whole range of things that create a fingerprint of a human being on the internet. So what's been shown is that just by looking at DNS queries, you can fingerprint individuals and you can re-identify them as they move across networks, because their DNS queries are so characteristic that you can figure out who it is that's moving around. On top of this, there was some other interesting research that said, okay, that's all well and good, let's encrypt recursive to stub. It turns out DNS traffic is so characteristic in terms of its timing and size that even that alone isn't enough. And if you have an observer who has enough visibility downstream of recursive to see encrypted traffic and upstream to see the clear text traffic going to an authoritative, you can still correlate the activity and you can still identify individuals within those traffic patterns. So we need to do more than just simply encrypt. And as I mentioned, operators can also see your queries and log them. So if you were thinking your DNS behavior really didn't reveal anything about you, well then, Toto, we're really not in Kansas anymore. There's lots going on here. And it's really, really, really underreported. Think about the last time you read a magazine article talking about how to secure yourself on the internet that mentioned DNS. They talk about encrypting your phone, encrypting your disk, using HTTPS if you can, going to Tor, all these things. But I haven't seen one article yet that puts DNS within that overall perspective. So this is trying to summarize the situation in terms of the risks that you have. So queries that are going on the wire can be passively monitored and actively monitored, both between stub to recursive and recursive to authoritative. And also there are risks associated with the data at rest. Okay, so just to start the story by going back to 2013 and talk about what were the privacy options at that time. Well, there were no standards for how to do DNS privacy at that time at all. There were a few protocols that had been developed and deployed, but some of them come to the IETF installed, some of them hadn't even gotten here. The main ones were DNS Curve, which was really designed for the recursive to authoritative communication, and DNS Crypt, which was stub to recursive. DNS Crypt is still around today. There are implementations. It recently got picked up by the Yandex browser. So it is around. But one thing to remember is these were developed really as anti-spoofing and anti-DDoS devices. They weren't designed with privacy as the primary design goal here. You kind of get privacy as a byproduct from these things. The Unbound recursive server also implemented DNS over TLS in 2014, so that's been around a while. But again, this was just sort of a side effect. They really did it as part of their DNSSEC trigger project because it gave them a tunnel to access a DNSSEC aware recursive if port 553 was being blocked. So it was a really mixed bag at that time. There was no standard way to do this. That's where the IETF came in and the Dnspriv working group. So Dnspriv was formed in 2014, and clearly you can see it had a really big job in front of it. So the first thing it did was try and narrow down its charter. And the original decision was that it should focus just on that stub to recursive step. And you might say, well, why not have multiple avenues of protocol development? And the answer was, let's not try and boil the ocean. This is a really tough thing to solve. The stub to recursive is where most of the information is revealed. So let's target that first. And then let's use what we learned doing that to move on to the recursive to authoritative. There's also some differences in trying to solve those problems, primarily in terms of authentication. So as an end user, somebody with a stub resolver on their machines, you tend to have a relationship with a few recursive resolvers. So it could be tens, you know, between work and everywhere you move. But in most of those environments, you actively choose to use that recursive. In a coffee shop, you actually choose to join the network with all its faults. The situation for a recursive resolver is quite different. It has to go to whatever authoritative it needs to resolve that query. So it essentially has no control to the set of upstreams that it has to talk to. And that makes creating an authentication mechanism much, much harder than it does in the stub to recursive case. So the first piece of work that the Dnspriv really did was to produce a problem statement. RFC 7626, I really recommend this. It's really well written, it's really good reading. And it does in much more depth what I did in a few slides, which is to walk through the ecosystem of the DNS and to present all the places where there is risk and leakage of information. One of the key things that I think this document does is it tackles that question of the alleged public nature of the DNS. And what it says is, it's correct to say that the data in the DNS is public, but individuals' transactions in the DNS are not and should not be public. And the analogy it uses here is, well, the content of the websites for Alcoholics Anonymous is public, it's a public website. The fact that you as an individual visited that website is not public data, and it shouldn't be. The next question the working group had to answer, having tried to scope out the problem, was there was agreement to encrypt the stub to recursive. How do we do it? The working group spent quite a lot of time churning over a variety of options, not just these ones here. They looked initially at Start TLS because that could be done on port 53. For various reasons, people then started favouring getting a new port and using TLS or DTLS. And you might think, looking at this, that actually DTLS is a natural way to go for DNS, given it runs over UDP. But when people started digging into this, a few issues were found with things like fragmentation. But also one of the key things is that if you try and do DNS over DTLS, you run into exactly the same problem as you do over UDP, which is a big response can't fit in a single message. So you have to fall back to an alternative transport. And the obvious one to fall back to is TLS. So the discussion went a bit back and forth, and the decision was, let's not go down this two protocol route again. Let's just start with TLS and get that right and choose a single protocol. So what emerged from the working group was that DNS over TLS became a standard, and DTLS became standard with experimental category. So choosing your encryption protocol is one part of the process. There's another to-do list if you're going to fill out this picture. One is you have to actually get the new port you wanted. The other one is you have to address the fact that historically, TCP implementations in DNS servers absolutely sucked. Because they were only used as this once-in-a-while fallback mechanism, no attention was really paid to doing them properly. And if you're going to move a step further and use TLS, then you have to address that. There's also a new problem for DNS in terms of authentication, which is bootstrapping. Of course, when you go to a website, you know the name of the site you're going to. With DNS, when you go to your recursive server, you typically only have the IP address of it. So that doesn't give you a natural mechanism to do authentication. So we have to find some solutions to that. And as I mentioned before, we still have to deal with traffic analysis. So there was a lot of sort of skepticism in the working group initially about whether we would get assigned a new port, but actually IANA recognised this was a really concrete use case, and actually in October 2015 they assigned port 853, and so both TLS and DTLS can run over that port. The next one wasn't quite so easy. This was to go back and look at what DNS servers did with TCP. What they did was they tended to do one-shot TCP. If they had to fall back to TCP, they opened a connection, fired off a query, got a response, shut the connection, went straight back to UDP. So using that kind of implementation was just unfeasible. There was a really poor perception of TLS as well, sorry, TCP, because all the performance tools that were used were based around this one-shot mechanism. So they made TCP inherently look, at least an order of magnitude worse than UDP. DNS servers had really, really basic capabilities. They often were hard-coded to only have 20 connections and have like a 1-minute fixed timeout, and that was it. No other defense mechanisms in there. So it was very basic. And DNS. Yep.
I could just add one quick thing too. The servers really didn't care for it because all the state had to be kept on the server around connection close.
Yep. So.
Didn't make the slide, but that was a big issue for why a lot of servers would implement.
Yes, yeah, that's true. So, and I mean, in general, the server operators didn't want to do TCP, so they wouldn't tune for it. They had no robustness. They treated it as a second-class transport, I think is fair to say. So To fix this part, they really had to revisit the specs. So the first thing we had to recognize is that the DNS people are not the first people to try and do TLS. There's a bunch of people out there who've been doing it for ages, so we should just piggyback on what they've done. So latency is an enormous concern in DNS. So connection setup, we needed to be optimizing what we did by using all the available techniques. So we needed to be using TCP fast open, we needed to be using TLS session resumption, and of course we started rubbing our hands when TLS 1.3 started coming over the horizon, because of course that was targeting things like 0 RTT and 1 RTT resumption. So that looks good. We also had to directly tackle the DNS standards. So there was an RFC in 2010, which was actually the first time it was mandatory to implement TCP for DNS. Before that, it had been a sort of fuzzy option. That RFC was bizzed in 2016, and in that, it basically said, don't do one-shot TCP. If you're going to do TCP, do it properly. Open a connection, pipeline your queries over it. As a server, when you receive it, you should process all your queries concurrently, and then you can send them back in whatever order you have the answers ready. And clients, you need to be ready to get those answers out of order, because in about 2015, the survey was all the top DNS client implementations couldn't handle getting answers out of order over TCP because they simply never thought a server would send them like that. We also developed a signaling mechanism so that clients could signal to servers that they wanted to keep connections open, because that was completely absent from DNS signaling. And of course, as I mentioned before, there's loads that we can learn from the HTTP world in terms of just generally improving what servers did here. So this is, for example, one of the simple things that got fixed in that spec, which is that traditionally servers, when they were listening on TCP, they picked a query off the connection, resolved it, sent it back, and only then did they look for the next one. And of course, resolving that query could take a long time if they didn't have any of the path in cache. So the simple fix was to tell servers, no, you need to be doing this more intelligently, pick the queries up and process them concurrently, and that's going to take a whole RTT off the client time. And the goal here was actually to work towards trying to get performance on a par with UDP by combining all these changes to the protocol and persistent connections. So to move on to this question of authentication, clearly we can't go from where we are in a single leap to everybody's using UDP today, everybody's going to use authenticated TLS tomorrow. That's just not going to happen. So what the draft that's currently going through Dnspriv suggests is being able to do authentication in two ways, and they're called usage profiles. So one is called strict, which is you must have both an encrypted and authenticated connection to your server, or you just don't do DNS. So this is the sort of purist approach, but it's also the protectionist approach. If you are somewhere where monitoring for DNS queries could imperil you, then you want to be able to have a level of security that they're just not going to be monitored. So strict is where you would go there. And we hope that this will become the default longer term. As we move towards it, though, we need a pragmatic solution, and that's called opportunistic. So in opportunistic, what you do is you first and foremost, you try to get an encrypted and authenticated connection. Only if you can't, you're willing to fall back to do just an encrypted connection. And this at least protects you from passive monitoring. But there's a third fallback, which is to say, if I can't do either of those, then I'm willing to fall back to clear text, because that's no worse than what I'm doing today. But as you can imagine, as the deployment of DNS over TLS increases, the state to which clients will fall back will hopefully become higher and higher through that list. So I mentioned the other problem is that you need additional information if you're going to authenticate your DNS server, because typically a client only has an IP address. So the current draft proposes two ways to do this. You can either configure an authentication name into your client, which in some ways is easier because it can be human readable, fairly easy to check. The other mechanism is to use an SPKI pin set. So again, we're borrowing from what's already been done in HTTP. So that can be a little harder because it's not human readable, but it can be a little more flexible in some ways to allow for key rollover. But of course, you might be saying again, these are the DNS folks. These are the folks who dreamt up this DANE thing and keep telling us all of us to use DANE for authentication. So shouldn't we, the DNS people, really be drinking our own champagne here? Well, the draft does also go through the details of how to do authentication via Dane. You still need an authentication domain name configured into your client to start that, but once you have it, you can do Dane to get the queries. In fact, all this work prompted a new solution for TLS in terms of Dane called the TLS DNS chain extension, and I'll just walk you through that. So this is how you traditionally do Dane as a DNS client. So you would have some configuration information that told you where your cursor was and what its authentication name was. As a client, as a DNSSEC validating client, you would go off and opportunistically, because that's all you have available at this bootstrap time, do lookups for Dane records. Then you get the Dane records back and you're ready to make the connection. You do a traditional TLS connection, getting the certificate or key information from the server, validate it against the Dane records, and you're good to go. The new proposal that's still going through the TLS working group is based on the recognition that, hang on, this thing I'm talking to and I'm trying to authenticate, it's a DNS server, it knows about Dane. So rather than me going getting the records as a query, I'll let it do the work. So you start from the same position in terms of configuration. However, this time it's the server that makes sure it has its own Dane records. What that means is, with the new extension, the client can signal in the client hello that it is capable of validating Dane records it receives in the TLS handshake. Knowing that, the server can send back all the Dane records necessary, and that's the entire chain, for the client as a DNSSEC validating client to do the work during the TLS handshake, decide that it can authenticate, and again, it's good to go with DNS service. The nice thing here is it reduces latency because everything's happening within the handshake, and it eliminates the need for that set of opportunistic lookups before you can even start the connection. So this is quite a nice technique. So to circle back and summarize what has been achieved in, and this is specifically in Dnspriv in the last 3 years. So we have a standard for how to do DNS over TLS. We have another standard that tells us how to pad our queries. I'm not going to go into this in too much detail, but this basically ticked number 4 on the to-do list. And I quite like this because what happened here was that EDNS 0 option that was being used in some cases to expose user data has kind of been taken back from the dark side, and we're actually using it to put our padding in exactly that location so we can obfuscate the sizes of DNS traffic. We have an experimental RFC for how to do DNS over DTLS, and we have a draft describing all these authentication mechanisms, which is in IESG last call at the moment. So looking back, for 3 years, that's not bad going for a working group. Okay, we haven't solved all the problems, but we've come a long way. And what the working group now is looking towards is tackling that recursive to authoritative step. There is an expired ID that proposed a few options that is probably going to be revived in a slightly different form, narrowing down the set of options to look at. The working group is probably going to consider rechartering. And also one of the things they want you to feed into that is data on what's happened today on the recursive to stub link in terms of implementation and deployment of DTLS. So there's still a bunch of work to do, but we're getting there. Lots of work has happened outside of the Dnspriv working group too. You remember I mentioned this kind of schoolboy error of, oh, you're leaking all the information in every lookup. So there is an answer to that now, and it's called QName minimization. This basically says only send the part of the query to the server it needs to give you the correct referral. And this looks really rather trivial and obvious, but actually the devil is in the details here. There are lots of corner cases, there are lots of little nasties hidden, and some of them weren't found actually till the spec was implemented. But most of them have been resolved, and there are implementations of this in Unbound, in Not. It's going to be in the next version of Bind, so it is being much more widely used, and hopefully this will become the default mechanism. There's a bunch of really interesting work going on about doing DNS over HTTPS. One of the potential upsides of doing this is that clearly, given there's a dedicated port for encrypted DNS, if somebody wants to block your DNS, your encrypted DNS, they can just block port 853. Whereas if you're using DNS over HTTPS, there are mechanisms where you can then run over 443 and somebody would have to block that port and all your HTTP access to defeat you getting encrypted DNS. A good few years ago, rather under the radar and with a proprietary implementation, Google published a DNS over HTTPS API. If you have the slides, there's a link to the service there. You can go and look at it. There's a nice little GUI. You can play with it. It was targeted at applications that wanted to do very lightweight DNS lookups. So it's interesting. It's different. To my knowledge, it never progressed through the standard side. What did progress through the standard side, and actually there's been a lot of flux in the drafts here. Quite a while ago, there was a proposal to do DNS over HTTP in wire format, and this is essentially a tunneling mechanism. So you're not changing anything about HTTP, you're just embedding wire format DNS in it. This draft is still active. There are several implementations, several servers out there if you want to use this. But what has come along much more recently, which I think has some really interesting potential, is a proposal to do DNS over HTTP2, doing it as HTTPS. And this is really about doing it in the sense of query origination from a client directly using this mechanism. And this is done in a much more naturally HTTP way, and it takes advantage a lot of the HTTP idioms. So what this essentially means you're doing is mixing DNS queries and HTTP queries on one connection. So again, this gives you the ability to do a couple of things, to hide your DNS queries, but also to get your DNS answers from the server that you're currently connected to. And this has a lot of interesting propositions. So having a look at that and going to the working group as well is worth considering. Something that's happened recently, but is really in a very, very embryonic state, is talking about doing DNS over QUIC. How many folks in the room are familiar with QUIC? Most of you. Okay, yeah. So QUIC's a developing protocol. It came from Google. It's being used in the wild in its experimental form. The things that make it attractive for doing DNS are that even though it runs over UDP, it's reliable. It has all those mechanisms built in. It's also low latency, so it should tick a lot of the performance boxes for DNS. The things that it also gives you over doing plain UDP are you have increased source address validation over doing UDP, which is very important in DDoS mitigation for DNS. And it also doesn't suffer from the problem of hitting an MTU limit and needing a fallback to a second transport. So this can be a standalone solution. And of course, the killer feature for privacy is that it's encrypted. There is no unencrypted version of QUIC. So doing this naturally gives you privacy. So the last place I want to talk about in terms of other work is really around data handling. And this is where I think the focus probably now needs to shift. We've done a lot of the standards work on the protocol side, but really what hasn't been tackled is what happens about the data handling. How many folks here have read the small print of their ISP and actually know how long their ISP retains their DNS data for, whether they anonymize it and whether they sell it to a third party? I do, because I asked the question, so I make sure I read mine, but typically it's not something you do. Life's too short, right? Except with changes in legislation, for example, the rollback of net neutrality in the States, that landscape could really, really change in the next few years. It could become normal for operators to sell your DNS data. So there needs to be attention paid to things like government policy. I live in the UK, we have the Snoopers Charter. That gives my government access to my browsing data, whatever that means legally, which I don't know. So there's government policy and there's government practice that we need to be considering. What would be great is increased transparency from providers. What I would like to see is that you get privacy by default and you can opt in to share your data as long as it is explained correctly, what you're buying into there. We also need to be paying attention to cases where operators say they shared data and it's been anonymized, to be sure that it's being anonymized correctly, because a lot of that is done in a rather ad hoc fashion today. And a lot of data gets shared for things like research through databases like passive DNS. And again, we need to be ensuring that that's done in conformance with proper data anonymity. Now, a lot of this work is probably well outside the scope of the IETF, and it's not really technical solutions in all the cases. But without solutions to this work going hand in hand with encryption on the wire, we won't have the full picture available. So to come back to that matrix I had earlier on and talk about which parts of it we can mitigate with the work we've done to date, well, we can encrypt stub to recursive to protect against passive monitoring. If you authenticate that, then you're protected against active monitoring, which is good. For the recursive to authoritative, we can do queue name minimization, which at least mitigates the leakage of information. And we need to still do more work on tackling data handling policies and practices at rest. I'm going to very, very briefly talk about service discovery because it is DNS, but a lot of people don't realize it's DNS. So service discovery is a mechanism that's used to discover services, and very often it's done on local networks, but there's nothing that limits it to a local network, and very often implementations leak information on a global scale because they do lookups out onto the network. So in this situation, one device advertises a service and it allows others to discover it. Sounds all well and good. But what's common in terms of doing this is that you give your laptop a name and your laptop uses that name when it advertises your services. So you may, some of you who can actually look on the network right now, you may be able to see devices on the network that are sharing in this way and figure out, it could be, Bob's phone as well. So the thing here is that what you're doing is you're advertising a lot about your personal devices. So not only is your name attached here, the set of devices you have here is advertised and the set of services you're advertising. So in situations like a coffee shop where there's like 10 of you in the room, go through the thought experiment of sitting there looking at this and being able to identify each person by looking at what devices they have and whether they're male or female or various things like that. And that's what you can do very easily. What people who really know what they're doing with this can do is drill down into the details of which services advertised with which parameters. And this allows fingerprinting of devices. And there's research that has shown you can fingerprint down to both software and hardware, even to software versions, because bugs get fixed and you can see, oh, they've got the version before this bug got fixed. So again, this allows fingerprinting of individuals and re-identification through something that people see as a very, very benign mechanism. The good news is that the DNSSD working group are also working on this problem. They've recognized it. It's a different problem to solve. They have some drafts recommending this. So if you're interested, come along to that working group later this week. So now I want to skip on to, we've done the standards work, where are we with implementation? So one resource I want to direct you to is the dnsprivacy.org website. So the goal here is organisations interested in promoting DNS privacy to be a central reference point for where we are in the evolution of this. So various people are involved in this. So Synodon are involved, NL Labs are contributing a lot, Salesforce, there's too many to mention here. Lots of individuals are contributing and we're getting grants from a range of organisations. So the kind of things that we want to do here is be a first-stop shop for what's going on with DNS privacy, how can I help, how can I protect myself. So one thing we're doing is trying to keep track of the state of the implementations in the major open source DNS name servers. So you can see here that Not Resolver is doing really well. They have a bunch of stuff available. Unbound is really close behind. Bind has chosen not to implement TLS natively inside the name server. What they are proposing instead is that if you want to deploy this, you do it by putting a proxy in front of your name server. And there are lots of proxies out there, Nginx, HA proxy. The Bind have actually produced an article in their knowledge database for how to put S-tunnel in front of Bind. And this can work really well, although there are some disadvantages because, of course, that load balancer isn't DNS aware. It's rather blindly passing through some DNS options that would normally be catered for by the DNS server. Additionally, it means that the source IP address of the query doesn't make it to the server. So some of the features in the DNS server, like ACLs, can't work effectively because they don't know where the queries are from. Everything looks like it's coming from the proxy. And there are actually some drafts proposing mechanisms to mitigate that and pass information from these general proxies to a server. What would be nice is if we got TLS support in DNS dist. DNS dist is a DNS load balancer, which has a huge range of features. It's a really nice piece of software. A lot of people use this in front of server farms to distribute queries. There is a feature request into this, and I have heard encouraging noises from the PowerDNS folks saying they're working on it. I personally think if we had this, it would be a game changer in terms of running servers, because people would feel confident about using it, and it seems like a really natural solution. On the stub side, the picture's a bit more mixed. There's a relatively new DNS library called GetDNS, which has really tried to become fully featured in terms of what it takes to do good DNS over TLS, and I'll talk about this more in a minute. The other implementations are there and they're catching up. To my knowledge, there isn't a TLS implementation in a native resolver library on any of the OSs that's officially supported and released today. That hopefully is also changing. So in that picture, the summary of where we are in terms of implementation status are that there's better TCP handling in DNS servers. There's been a very encouraging uptake of QNAME minimization. There are several implementations of DNS over TLS. What we haven't seen yet is any implementations of DNS over TLS. I'm not really sure why, but the interest has really been focused on TLS. And as I mentioned, there are implementations out there doing a form of DNS over HTTP. To move on to where deployment is, we have today experimental servers that are available. We don't have any large-scale deployments. I am aware of 2 or 3 organizations who are planning to do that in the next year or so, so it's on the way. But at the moment, we have a set of 12 experimental servers that use a mix of software. The information about all these servers can be found on the Dnspriv.org website. Oops, that didn't work very well. That block shouldn't be there. There should be a nice pretty page under there showing you a monitoring page with lots of green and red blobs for each of the servers. My animation clearly failed there. So if you want to see the status of those servers, you can go to this stage and see it. And it also tries to tell you some of the capabilities, for example, whether they're doing QNAME minimization, whether they present through some mechanism authentication credentials that you can use to do strict privacy, things like that. The thing I did want to announce with my last minute addition to my slide was that for the first time at this IETF, the network operations team are running 2 DNS over TLS enabled servers through the IETF network. So if you do want to start using this and playing with it, then we have local servers to do that. And I believe the information for that is on the meeting network page. And if it's not, come find me or email me and I can share that with you. And have I had an even more epic fail? Let me just. I think that was just a minor freeze. Okay, right. So that's the story on the server side. What's the story on the client side? As I mentioned, the best place we can recommend you to go today is to use Stubby. Stubby is an application that works as a privacy-enabling resolver on a local machine. It's based on the GetDNS library, and it's really a wrapper around running the GetDNS library as a daemon. There's a user guide available to help you get up and running with it. It came out in the best place. You shouldn't take anything less than the 1.1 release of GetDNS if you want Stubby. It runs as a daemon locally, picks up any queries that go to localhost. So by reconfiguring your system resolvers to send queries to localhost, they will all get picked up by Stubby and proxied out over TLS. And it comes with a default configuration which uses a subset of the servers, the experimental servers that I mentioned earlier. Oh boy. Okay, my laptop doesn't want to play. So I'm nearly at the end. Let's hope we can make it there. So Stubby is currently in a prototype stage. We're kind of saying it's for advanced technical users. It's not for everybody yet. It does support all the features we talked about in terms of choosing between strict and opportunistic and choosing between a name or PIN authentication. A word of warning, we are actively working on evolving Stubby, and some of this work happened at the hackathon this weekend. We're going to separate Stubby out. At the moment, it's basically a tool that comes with the GetDNS library when you install it. We're separating it out to be its own standalone application. We're rewriting the documentation, redoing all the packaging, etc. So if you go and look at information related to Stubby, it probably will evolve in the next few weeks as we do all that work. We're also working on, we have a homebrew tap at the moment, which should be a formula hopefully next week. We have Docker images, and we are in the early stages of thinking about what a GUI on this would look like, because if you want to make this accessible to non-technical users, you have to think about that. So we have a GUI that I'm happy to demo to anybody who's interested. Given my flakiness of my laptop, I don't think I'll try a live demo right now. Basically, it's a little control panel that lets you run Stubby as a service, gives you a button that flicks your system resolvers. You can look at the configuration, which at the moment is an ugly configuration file. That's going to get prettier. And you can see a log. And what we log is the opening and closing of TLS connections to all your upstreams. And you can configure multiple upstreams and distribute your queries among them. So as I said, this week at the hackathon, there was work on Stubby. There was also some work done by folks in the room starting an implementation of how to do the Dane method of authentication, and that included doing it using the TLS extension. And there was also some really good work starting support within Android to do an opportunistic form of DNS over TLS, and I'm really excited about that. So I want to thank the guys who did the work, because I think that that's a really important step in making this more broadly available. But it does bring an interesting question, which is, how do we make this usable? So the thing is, DNS privacy is going to be a completely new paradigm for end users. Think about how much people struggle just with HTTPS, to not going to insecure websites, and think about all the effort that's been put into getting the icon just right, the server certificate warning messages right. There are whole teams that do nothing but work on how to make this work for non-technical users. So people are barely grasping HTTPS security. Suddenly telling them that they have to worry about DNS security as well is going to be a real challenge in terms of communication. And another challenge to add on to that is that message is probably going to be coming from DNS folks who really aren't used to dealing with end users. We're used to having DNS under the hood and just work. So I think that will be a really interesting dynamic as those two worlds meet. To make this succeed, what's come out of the HTTPS world is this concept of, not just that world, but all the studies into things like trying to make email encryption easy, a whole variety of different places, is you have to have something called usable security, which it means that a really nice good UI isn't good enough, because users if they don't understand what they're doing, they can still make huge mistakes, even with the best of intentions. And even if they do know what they're doing, they can still make mistakes. So you have to basically do everything you can to protect users from themselves and enable them to get the privacy they want. So this is a non-trivial problem that, again, is probably not for the protocol folks, but has to be solved if this is going to become realistically rolled out. So to summarize, these are what I think are the key challenges short term. So one is awareness, both among technical and non-technical folks. The second is clients, is getting usable clients and getting DNS over TLS support integrated into operating systems. Usable clients for non-technical users. We are still held back by not having some wide-scale deployment of servers, but I think that is coming. As I will keep banging on about, I think we need much more transparency from operators in what they're doing with DNS. And of course, the big problem to solve is still recursive to authoritative. So to summarize, DNS privacy is a real problem, and it's one that most people aren't aware of. And I think you hear many of the discussions, many of the political clashes between the human right to privacy needing to being protected against government's desire to wanting to have a backdoor into encryption. And DNS is not alone, but I think it's becoming increasingly caught up in that discussion. It's a very large solution space, and it's not going to happen overnight. It's going to be years before we get there, but we have made progress. You can do DNS privacy today. And that situation is improving, because I really think over the next year or so we will see a lot more DNS privacy services emerging. So with that, I think I'm out of time, although I hope there's time for a few questions. So I'll thank you for your time today and take any questions from the floor.
Hi.
Hi.
Chris Seal. With DNS over HTTP, is the idea it would come from the same website that you're browsing then?
That's one of the use cases, yes. So you're connected to LinkedIn, and LinkedIn gives you your DNS. My
question on that therefore is, I'm therefore trusting the same, if I'm on a malicious website,
yeah.
I'm in a world where I can't tell from domain names or anything that I'm in a malicious world of poison DNS throughout. So how do I know that I've got?
So my understanding after talking to one of the authors of that draft is that the current draft is basically specifying the transport, just the way you do the transport. What is a separate question is, what's the requirement to DNSSEC validate the answers you get back?
Yeah, it's just obviously part of the beauty of DNS is it's an independent authority of name resolution.
And it's, when you talk about doing it over HTTPS, I find it interesting because it is shifting that model to saying that you can get your DNS from a variety of places. There's an argument that says you may want to restrict doing that to sites you have already authenticated with HTTPS, in which case you have some context, but the details of that aren't clear yet. You're quite right, and it's a very good question.
Yeah, it's back to the if we don't trust websites in the first place, why would we trust them with DNS?
And and you have to, and it also comes back to you have to trust somebody.
I know. It comes back to your usable security.
Yeah.
I could see it actually making things worse because I get a phishing email and I hover over it and it's easy to spot because the DNS is wrong. Now in future the DNS will look right to me because everything about it looks right. It's all because I started on a website somewhere that I thought was correct.
Yeah, so there's a lot to detangle there, I think, before that's deployable.
And so speaking of things we bang on about, that was actually a segue into my personal peeve is this term DNS over HTTP. Because it means different things to different people. And you presented kind of the DNS world view of it. The web browser people have a very different view of what it means. And those views are strongly opposed to each other as far as the involvement in DNS servers and validation and generating in what the data represents. And unfortunately, I haven't myself come up with better nomenclature about it. And until we have better nomenclature to reflect the two different views of what the term even means, you just have to be excruciatingly clear. And in this particular case, it wasn't. It crossed that fuzzy boundary of, well, which are we just talking about encapsulating the DNS protocol through the HTTP transport? Or are we talking about how a web server delivers address information to you? So
yeah, no, that's a good point, and I think probably could have been clearer here. And it's very good to take on board. You're saying yes, I looked at it with a DNS point of view, and maybe it's DNS in HTTP or something like that rather than over for the second one. But I think the draft actually specifically uses that title, DNS over HTTPS, and I agree. It's in and again I sort of worry a little bit about, as that progresses, it getting enough cross working group review with all that input there, because it isn't clear, and I think the use cases are evolving for it as well, frankly, just as the spec has. So I'd be really interested to see where that is in, say, 6 months, like what's emerged from review.
And that's the same thing about use cases too. The DNS people have a very different use case from what the browser.
Yes, yeah.
Hi, Sarah. This is Mohit Batra. I am from National Internet Exchange of India, and I am also an ISOC fellow for this IETF meeting. So my question is the DNS privacy solution being discussed at Dnspriv working group applicable to the .onion top-level domains, which are used for browsing darknet websites?
In what context do you?
As far as I know, the .onion is a top-level domain, and its resolution does not follow a simple path that is from stub to recursive and recursive to authoritative. It follows a different trajectory altogether. I mean, it does not follow the normal DNS resolution.
Yeah, that's because it's not normal DNS.
So my question, I don't know whether it's a valid question or not, but still, just to clear my doubt, whether this DNS privacy solution is applicable to the .onion top-level domains or not?
It is and it isn't, right?
Well, QNAME minimization.
Yeah.
Right? And that's the one thing that helps. Because the problem is if you're leaking your fully qualified .onion domain names, you're leaking a lot of information there,
Yeah.
whereas the roots can cut off .onion at the knees, and then it falls out of the monitoring of the DNS system.
I'll just repeat that to the mic. So the point was that probably the biggest thing that mitigates in that circumstance is using QNAME minimization so that the full query doesn't go to the .onion servers. So reducing data leakage in that fashion. But of course, we're only talking today about a solution that works stub to recursive, not recursive to authoritative. So QNAME really is the only mitigation you have on that path. There's been, what might be helpful is there's been some interesting work on the fact that Tor is actually leaking information because it does clear text DNS out of some of its exit nodes, which they've realized is a data leakage, and they're now interested in using DNS over TLS for their DNS resolution because they hadn't really recognized it as an attack path, but they have more recently recognized that. So I hope, is that helpful?
Okay, I'll just do some more homework and get paid back to you later on.
Yeah, we can talk offline.
Okay, thanks.
Okay, so I think if that's all the questions for today, thank you very much for your time, everyone. And I hope you all go forth and use DNS privacy. Please do.